First thing is, as I said, Dirk has given me 30 minutes for this presentation, but we've got a lot to go through. This is not going to be a real salesy presentation. We're going to be covering a lot of engineering data here, and so I'm not sure I'm going to have time for questions. If you've got questions, you can see me afterwards. You can send an email to info@scannermax.com. We've set up a new website for these scanners, www.scannermax.com. Up there you'll see an arrow pointing to the forum. You could post questions on the forum, any challenges you have for me. I'll be happy to answer your challenges up on the forum. So without much further ado, since everybody here is interested in faster scanning, let me first talk about what ScannerMax is. ScannerMax is a division of Pangolin Laser Systems. Pangolin Laser Systems has another division called Lasorb, dedicated to protecting laser diodes from ESD. So we set up a new division of Pangolin to help us to distribute scanners with the maximum performance, and hence the name ScannerMax. Now, we didn't just decide that we're going to get into the scanner business kind of overnight. The scanners that we're developing are based on more than 2 decades worth of research. And over the course of that more than 2 decades, more than a dozen patents have been issued. If you go up on United States Patent and Trademark Office, if you go to the German Trademark Patent Office, if you go to the China office and you type in William R. Benner Jr., the internet's going to light up and it will let you know what we've been working on over the past 2 decades. And so what we spent the last 2 years on is figuring out how it is that we're going to actually build these things. And so since we're all interested in faster scanning, I figured it would be worthwhile to talk about what is scanning speed in the first place, and oh, by the way, what's all this K stuff about that I've heard. So what a scanning system is supposed to behave like is a 2-pole low-pass filter. And that is, it's a system where on the low end of the scale, it has kind of the same response, and as you get higher and higher and higher frequencies, the frequency goes down, and as you can see, it's kind of wiggling. We're going to be talking about the wiggling here in a little while. But at some frequency, it kind of it starts to transition. And everybody who creates filters, there's a standard and filter kind of terminology of what we consider to be the cutoff frequency of the filter. And the general agreement is that we designate the filter bandwidth as the point at which its output drops -3 dB. Now, that's a fancy way of saying that when its output drops to 70% of its ordinary response. So that's what a low-pass filter is, and that's kind of how we characterize low-pass filters. That's what scanners are supposed to behave like. So how do you measure that? Well, there's a couple of ways. You can use fancy test equipment like we have at Pangolin called a dynamic signal analyzer. But a much more easy way to measure that is to use the Ilda test pattern. And the Ilda test pattern gives us a couple of tools with which we can measure speed. The most prominent of those being right here in the center, this circle and square phenomenon here. Now, one thing about this, everybody here is familiar with the Ilda test pattern, but people may not have actually stopped to take a look, but there's actually 12 points in the circle. So it works kind of like a clock. And so what that means, and the circle represents like a sine wave on both the x and the y axis. And the sine wave is a great tool to characterize filter response. And so what this means is if we're putting out the Ilda test pattern at 12,000 points per second, since there's 12 points in the circle, if we put out 12,000 points per second, that means the sine wave rate that's coming out of the Ilda test pattern is 1,000 actual cycles per second, or 1 kilohertz. What happens is we got the Ilda test pattern, and everybody says you're supposed to put the circle for the Ilda test pattern inside the square. The actual data for the Ilda test pattern puts the circle outside the square, but we're supposed to speed the Ilda test pattern up so fast that the scanners really can't keep up putting the circle inside the square. Now, probably none of us remember from 7th grade geometry class that the difference between putting a circle outside of a square, touching all the corners, to putting the circle inside of a square, touching all the sides, reduces the circle's size by 70%. There's that number again. 70% happens to be 3 dB, -3 dB. And so the Ilda test pattern gives us a very cool, and convenient way of measuring that minus 3 dB point on the low-pass filter. So this is what we mean by K. If you have 30K scanners, what that means is that you will be putting out the Ilda test pattern at 30,000 points per second. That circle will be going 2.5 kilohertz, 2,500 times per second, and its response should be reduced by 70% as a result of this low-pass filter phenomenon. So, now that we know it's just a low-pass filter, that doesn't sound all that complicated. Why don't we just say, if we wanted to go faster, why don't we just turn it up? You know, just tune it faster. Do what the tool man does in the United States and just plug it into 220, right? Well, why won't that work? Well, there's two problems with that. The first one has to do with the mechanics inside the scanner. I've got a little animation here showing a laser beam coming into a laser to a scanner, and it's scanning. And at slow speeds, everything is fine. But as that scanner starts to speed up and gets faster and faster and faster, at some point, what will happen is the entire rotor starts actually wobbling. I used to think it was just the mirror, but it's actually, in some cases, the entire rotor that's wobbling. And when this happens, it tends to distort the images. Now, I'm sure there's experimenters in this room, people who have tried to tune the scanners faster, and you can tune them faster, all right, and they'll go faster, but the problem is that the images just start looking kind of not so good anymore. And so I have some actual images that I've taken just within the last few days with my iPhone, and these lines are supposed to be straight, and every single one of them is curved. This is unfortunately, my iPhone didn't really focus on this really well, but this is supposed to be a series of dots, and it looks like an upside-down tornado. Each one of these lines up here is supposed to be straight, and they start to look curved. It's a lot more clear in this test pattern here. What you can see is that these lines that are supposed to be straight are kind of wiggling around. And this is because of the mechanical phenomenon called the rotor dynamics inside a scanner. Like I say, for many years, I believed that it was just the mirror that was bending. And when we did some experiments in our own development, some of the things confirmed for me that I didn't understand the full picture. So we actually hired a guy from Boeing to do the analysis with some of the most software to help us to understand this. And I'll show you that to you in a second. But before I do that, I want to show you how scanners are put together and what's really contributing to this resonance. So this is a classic, your conventional galvanometer. This is the way they're all made today. You have a moving magnet rotor down here, a shaft, a bearing that's held in with a retaining ring. In many cases, there's a stopping pin right at the top of the scanner to stop that thing from spinning around and around. And you got the mirror way up there. So you have the magnet way down here. You've got basically a long length of metal. And if you take a look at the diameter of that, it's substantially smaller than the magnet. And so this is really a spring. The magnet's actually a spring. The mirror is a spring. It's all springs. So this whole thing is really full of springs. And so what happens here is that because the diameter of that rotor is so small, it becomes kind of like a loose spring. So as I was saying, we hired a guy from Boeing to help us to do this analysis, and we've done hundreds of these analyses, not only on our scanners, but on every conventional galvanometer we can get our hands on so that we can really understand what's happening and to the extent that it's happening out there. And with this software, you can tell what we call the first bending mode resonance, the second bending mode resonance, the torsional resonance. That's a resonance that tends to resonate back and forth like this, around and around. And our analysis is so complex that we even included the effect of the epoxy bond in the mirror. And that epoxy bond is rather menacing. And so what this analysis shows, and this is a conventional galvanometer that we all use, is that you can only get, but by the time you tune this thing somewhere is around 50 to 55K, it's really going to start, you're going to get into that resonance problem pretty good. So this is what I called short rotor with small mirror. Here's another one, and this is a long rotor with a small mirror. A lot of us use these scanners are about that long and still using small mirrors on there. Now in this case, it's mostly the moving magnets that's doing the bending and not so much the mirror. Now the way this works, folks, is this is really a snapshot in time. That's what we're looking at here. When this thing is resonating, it's kind of doing one of these numbers at a very high speed, of course. And in this case, because the magnet here is so long, it becomes a really springy spring, the resonant frequency of this one is only about 45K. So even though people try to tune these things up to 60K, you will get into trouble like this, and we can see this and see it in the Ilda test pattern. As soon as you cross 45K, things actually really start to bend. So here's another phenomenon. This is what I call long rotor with large mirror. This is a 5mm mirror, and while I was here, I've spoken to a lot of you about this kind of a scanner, and anybody who has these scanners has this kind of problem, has reported this problem to me. They say, Bill, it projects small text. This thing is waving. It's waving all over the place. Yeah, well, no kidding. This thing hits a resonance at around 20K. Greg Makoff has these scanners tuned up to 30K. So you can tune past the resonance, but the scanners actually themselves are only usable up to something like 20 to 24K before you get into this. Now, if you take a look at this one here is very interesting because you see a little bit of bending here happening in the magnet, perhaps a little in the mirror, but it becomes really obvious that all the bending is happening right there in the shaft. So after doing many of these analyses, what occurred to me is what we're talking about here is mechanical impedance. Now, we got a lot of electronic engineers in the room, and people understand from an electronic standpoint, it's an old saying, we've heard it in many classes, maximum power is transferred when all the impedance is matched. Well, likewise, in the mechanical standpoint, maximum resonant frequency happens when all of these springs are contributing equally. And what I've shown you is that there are cases where the mirror is doing all the bending. There are cases where the magnet's doing all the bending, and there are cases where it is the shaft that's doing all the bending. So that's kind of the first problem that we face with trying to go faster and faster with scanning. I said there were two problems. The second one is heat. This is a picture of the inside of a conventional scanner. If you were to take a scanner like this, and take a samurai sword and cut it in half right across the top, this is what you would see. A moving magnet in the middle, a solid steel outer core, and lots of teeny tiny turns of wire in here, somewhere between 50 and 75 turns of wire, small turns of wire in that gap that's called the air gap. The air gap is the gap between the magnet and the steel, not the gap between the magnet and the copper. So because of that, this becomes a great way to heat the magnet. And magnets hate heat. As the magnet gets hot, its remnants, its magnetism actually is reduced. And if you get the magnet too hot, it will be permanently reduced and permanently demagnetized. And what this illustration shows, and this is not just an artist's rendition, this is not a wishful thinking, a concept drawing. This is actual screen animation from engineering software that computes heat loads. And so what you see is as the heat's coming in, it's heating up the magnet. And the unfortunate thing for the magnet is the only way that that magnet can get rid of the heat is through what normally holds these wires in place with great scanners, which is thermal epoxy. And some of the cheapest scanners that are made in China, they don't have thermal epoxy. The coil is held in with super glue. So that magnet is in big trouble. Here's a formula. In the interest of time, I'm not going to get into everything about it. I will talk about the conclusions of this formula, which are, if you want to scan twice as wide, but at the same scan speed, what it's going to do is cause 4 times the heat inside the scanner. And if you want to scan twice as fast at the same scan angle, it's going to increase the heat inside the scanner by a factor of 16 times. This graph shows a conventional galvanometer operating at various scanner tunings. This graph assumes that the outside of the scanner is 40 degrees C. In other words, you're doing an outdoor show in Spain in the summer. And so the outside of the scanner is 40 degrees C. At 30K, the inside of that scanner gets up to 100 C, hot enough to cook, to boil water. Now at 20K, it's really not that much hotter than ambient. And at 10K, it's barely even noticeable, the heat inside the scanner. But at 40K, if you take a 30K scanner and tune it to 40K, the heat inside the scanner more than doubles. So this graph really shows 2 things. It shows why it is so hard to go faster and faster and faster scanning. One of the challenges, one of the what I call the barriers to faster scanning. And it also shows why it's so relatively easy, why on the lowest cost projectors we see 20K scanners, because that's really easy to do. The heat implications of that are not very severe at all. By the way, a little bit of trivia. Again, I know everyone's just gotten back from lunch. I see people stretching in there. And could anybody here guess when the conventional moving magnet scanner was invented? When this idea actually came into being? Any guesses? Christine? 1800s. No, not quite that far back. I would hope not. Anybody else? Boy, it is just... Yes. Here's the patent for it. It was filed in 1976. And what you see is here's the same moving magnet. Here's how you put shafts on the magnet. Here's a slot in the shaft for the mirror. Here's how you make the coils. This is an idea that's 40 years old. Now, doesn't anybody else think that somebody in the last 40 years would have found a better way to do this kind of thing? Shake your head this way. Okay, so I'll give you one more formula. This one's really easy. This is what we call our optical scanning formula for success. Stronger plus cooler equals faster. If you can make the rotor stronger, you can make the motor run cooler, that will allow us to get faster scanning. And not only faster, but more accurate scanning, because we get rid of the squiggles and the wiggles. So we'll show you how we're going to do that. So here's a comparison of the conventional moving magnet scanner rotor and our rotor. In fact, this is the most wishful thinking. This is the most expensive American-made conventional scanners made, and because the lower cost ones, this shaft's even smaller. So the difference that you see is that our shaft actually is nearly the same size as the magnet itself. By eye, you would not be able to tell the difference. Another difference is that we've removed all the parasitics. We don't have a stopping pin in our scanners. Our scanners will actually spin round and round if you let them. We don't have other parasitics, other things ground into the shaft diameter to reduce its strength. And one surprising thing is that the stiffness of a shaft like this, both bending mode and in torsion, goes as the 4th power of diameter. So just by increasing the diameter of the shaft by 50%, as we've done, increases its strength by about 5 times. In addition to that, we've reduced the distance between the magnet and the mirror. Here's the mirror, here's the magnet. And in addition to that, what we've done is we put kind of a back support on the mirror. So it's no longer a little mirror that's sitting in a slot, but it's kind of being held on the back as well, being supported in the back. So let's see what the results of that are in the resonance analysis software. Now what we see is that we see the mirrors bending a little bit, shafts bending a little bit. This is definitely bending. This whole thing is arced. So from a mechanical impedance standpoint, now we have kind of a very good impedance matching situation. Everybody's getting into the act here. You got both the magnet, the mirror, and the shaft all sharing this spring load equally. And because of that, you see the resonance, which was somewhere in the 50 to 55K range, is now 92K. Now, if you're close enough and paying really close to the screen, you'll notice the torsional resonance as well. Torsional resonance on a conventional galvanometer is 22 kilohertz. On ours of this size, it's 30 kilohertz. And it has a lower Q. It means it doesn't really want to resonate. And what this means is that with our scanners, in most cases, you will not need a notch filter to use our scanners. You will not need a notch filter even when you operate our scanners at a higher rate. So here's another situation, what we call long rotor with large mirror. And once again, you see that the mirror is bending a little bit, shaft's bending a little bit, the rotor magnet's bending a little bit, and all of these things are getting into the picture. The mechanical impedances are matched very well, and the result, remember the other guy's 20K, us 34K. So it's clear that we have made the rotor system stronger. Now, one of the analysis that we did was to say, well, okay, in the first case, the other guys, the mirror is primarily the bending thing. It's just simply too thin. How much thicker would we have to make the mirror in order for it to be stronger? All right, and so this graph on the left-hand side shows that that mirror would have to be something in the neighborhood of 1.5 millimeters thick, probably about double the thickness of a typical conventional galvanometer mirror. If it's double the thickness, it's actually double the weight. So obviously that's going to make the whole thing slower. This line up here showing the mirror. And the maximum, even if we put a 1.5 millimeter thick mirror on it, we'd still only get to somewheres north of 60K. Whereas with our rotor, partially in response to it having this back supporting phenomenon, partially in response to our shafts simply being bigger in diameter, we're able to get a much higher frequency even with a much thinner mirror. Our mirrors are 1 millimeter thick typically. We could actually reduce this to 0.8 millimeters thick and still be exactly the same speed as we are right now. So clearly the rotor is stronger. But what about the second problem, heat? Well, you remember here's the inside of a conventional galvanometer construction, and here's the inside of ours. We have the steel that comes a lot closer to the magnet, and because of that, the magnet produces more energy. You think about magnets on a refrigerator. Let's say you have a bunch of papers that you're stacking up, and eventually it won't hold the papers. It's not because the papers are so heavy, it's because the magnet is so much farther away from the refrigerator. So as the magnet gets closer to the steel, it produces more energy, more magnetism. Because of that, we don't need as many turns of wire. In our equivalent scanner, here's 50 turns of their little wire. We have 40 turns of wire, and you can tell that our wire is much bigger. Again, this is not an artist's rendition. This is actually a screenshot from engineering software. So let's see what that actually winds up doing. In the case of theirs, the heat's actually pouring into the magnet and has to get its way out through the thermal epoxy. In the case of ours, the heat, since the steel is actually surrounding the wire, it's sucked right off the wire itself. A little bit of heat does go into the magnet because there's close proximity of some of the turns to the magnet, but the magnet can get rid of that heat very easily because it's surrounded by steel. So it runs cooler. So that's what we're talking about here, folks. A series of stronger and cooler scanners that we call the Saturn Series. The reason is, as many of you know, my father was involved in the Apollo 10 and 11 missions to the moon, and the very first scanner that we came up with, we designated for 5 millimeters, and so I was looking for a name, and somehow the name Saturn V stuck, and so there we go. Now we've got the Saturn family of scanners. So we've got a family of 3 scanners, Saturn 1, 3, and 5, which cover between 1 millimeter and 8 millimeters in optical beam diameter. And we believe that these scanners deliver the highest performance attainable. So here's our Saturn V. It's great for moving large mirrors fast and wide. Our Saturn III is still experimental. I was hoping to bring that here, but some of the parts that were supposed to be delivered 2 weeks before I got here actually wasn't delivered until I got here. So we wanted to actually build this. Our computer analysis suggests that we can get to 90K with this scanner. And our Saturn I, which many of you saw operating yesterday, it's specifically designed for the 1 to 3 millimeter range. You think 1 millimeter, is that really even usable? Well, Harold Bollinger, if you come to the Pangolin User Group meeting, which is it tomorrow?
On the 7th at 4 p.m.
On the 7th at 4 p.m., you will see a laser, and I think at the trade show, Harold showed this as well. It's a laser that produces 100 watts in a 1 millimeter round beam with an M squared really close to 1. So you can do a lot of power with a very small beam. And not only that, but there's a lot of interest right now in self-driving automobiles and automobiles that can kind of take the burden of driving off you in some cases. And the way these things are doing it is with 2 millimeter beams, scanning the pavement and doing that sort of thing. So there's a lot of research and development in the 2 millimeter range right now. And so that's an area where we have designated our Saturn I. And one of the things about the Saturn I is it has the lowest inertia of any scanner I know of. It has a 0.010 rotor inertia. What that means is that the torque to inertia ratio, it just really wants to go fast as long as there's a small mirror there. And so the end result is that this is the easy way to 60K. Now, what do we mean the easy way to 60K? Well, on the left it shows the current way that we're getting to 60K. We're talking about pretty good size big scanner amps and a pretty good size XY block. And on the right shows our Saturn I with our new scanner amp, which is all digital. Now, I computed the amount of space that this takes up. This has 1/3 the volume and about 1/4 the heat. So our new amplifier is all digital, VSP based. It can run as a single axis driver or a dual axis driver. Mostly it will be used as a dual axis driver, I would suspect. It's a 400 megahertz floating point DSP, operates up to 260 kilohertz sample rate. So really fast, as far as I know, fastest in the industry. But that's not all we've been working on. We've got a universal mount concept. So for example, if you want to have a left incoming beam entrance or right incoming beam entrance, in our case, all that involves is unscrewing a couple of screws and screwing something onto the other side. It doesn't involve you buying another mount. And another thing we've come up with is making the mirrors have the same inertia. So we do this with shaping of the X mirror. In the case of the left, if you take a look, we have what we call our Darth Vader shaped X mirror. And on the right, we have a paddle shaped X mirror, which can handle 5 millimeter square laser beams, which are quite in use in this business. The last thing I'll talk about, I could talk about this thing for days, but is our bearings. It's made of a special nitrogen alloy steel called SV30. If you look SV30 up on the internet, you'll find two things. A couple of articles about bearings and lots of articles about chef's knives. This is used in the finest chef's knives. And we use a silicon dioxide ceramic ball. So it's hybrid bearings, and they're made in Germany. And you can see the left two is 440C stainless steel on the beach. This is chrome steel, and this is SV30 on the right. So this stuff lasts a long time. So the question? So we have set stock in 2014 such that just like we deliver quick show systems and LD2000 and beyond systems from stock, you'll be able to pick up the phone, get it FedEx the next day. We're trying to make it a no-brainer. So we were contacted by a company who said, we know you're making scanners, can you make cheap scanners? And I said, we're not really interested in that. We're concentrating on the high end. If I spend time doing a cheap scanner, I'm not going to be spending time working on our stuff. But before I hang up the phone, how many cheap scanners are we talking about here? And he said, 200,000 a year. And we're willing to sign a 6-year contract. And I said, well, let me think about that for a second. So we thought about it for a little while, and we created a scanner based on our VRAD 506 actuator platform, which is a really strong little actuator. And the net result of this scanner was really quite surprising. This thing performs with small mirrors just as well as CT scanners, as you saw at the trade show yesterday, just as well. But the difference is that since this has such a strong little rotor, still based on that 3mm rotor diameter, it's able to drive large mirrors, such as this 1-inch round mirror. This is not an artist rendition. This is actual performance. We can get 1 millisecond small steps out of a 1-inch round mirror with that small scanner. So it's quite remarkable, and they can be made very inexpensively. Now, we also think that this is the lightest scanner. There's one other company in China claiming to have a lighter scanner, but I can't get my hands on it to confirm that theirs has a lighter scanner or not. But our scanners, our little ones, have holes in the front of them, so they can be mounted from the front, which means that we can make an XY mount out of sheet metal instead of milled aluminum. So I'm sure that when you put 2 of our scanners with a sheet metal mount, that we're definitely going to be lighter than the other guys. So.
How much?
Well, we believe that we can make these scanners at a price that they can be put into literally every low-cost laser projector. And that's ambitious, but that's what we believe. So that's what we're targeting. For more information, contact me at the website. Afterwards, send me an email, buy me a drink, whatever you want to do. Thank you.